Hello viewers. So today our topic is continuity of a function. So today we'll see what are the conditions for a function to be continuous at a point A in its domain. So let us first take the definition of continuity of a function at a point, and then we'll take some examples how to prove the continuity of a function. So let us first take the definition. So a real function fx is said to be continuous at a point A of its domain if the limit x tends to a fx exists and equals to fa. That is, the limit of the function at x equal to a is equal to the value of the function at x equal to a. Clear? Therefore, fx is continuous at x equal to a if the left hand limit when x approaches to a and the right hand limit and the left hand limits are both equal to the value of the function at f equal to x equal to a. So if fx is not continuous at a point, if it is said to be discontinuous at that point. Clear? So fx is discontinuous at x equal to a in the following cases. For example, if the value of the function at the given point, which is a, is not defined, then the function may be discontinuous. If the limit x tends to a fx does not exist, clear? And if the limit of the function at x equal to a when x approaches a is not equal to the value of the function at x equal to a. Suppose we have the point x equal to a. Now to the left, say we have a point a, and to the right we have a point b. Suppose this point a is a minus h and this point b is a plus h. Now when we approach towards a from the left side, clear? That is, when we are approaching from those values of x which are less than a, then we find the left hand limit. Similarly, if we approach from right towards a, that is all values of x which are greater than a, then we calculate the right hand limit. Here h is a positive quantity and it is very small, but h is greater than 0. So a minus h and a plus h are the 2 points which are very close to x equal to a. Clear? So when we approach towards a, that is when x tends to a plus, clear? Here a minus, we are considering the left hand limit, so this is minus. So when x approaches towards a from left side, then we have the left hand limit. Clear? This is the left hand limit. Similarly, when we approach from right, then we have x tends to a positive fx, which is the right hand limit. Now for a function to be continuous at x equal to a, these two limits must be equal. So the left hand limit must be equal to right hand limit for this limit to exist. here we do not have any negative sign or positive sign, so it means both these limits exist and are equal, and both these limits are contained in this expression, that is limit x tends to a fx. Moreover, for the function to be continuous, we find the value of the function fx at x equal to a, and if fa is equal to this limit, then the function is said to be continuous. Clear? So what are the conditions for a function to be continuous? The left hand limit should exist, the right hand limit should exist, both these limits should be equal, and the value of the function at x equal to a is defined, exists, and equal to the left hand limit and right hand limit. So we can say that if left hand limit is equal to right hand limit is equal to the value of the function at x equal to a, then the function is said to be continuous. And the function, if we want to prove a function to be discontinuous, then it is sufficient to show one of the following results, that is if fa is not defined, and if limit x tends to a fx does not exist. What does it mean? This limit doesn't exist means if the left hand limit exists and right hand limit exist, but they are not equal. Clear? Not equal. And if the limit x tends to a fx does not equal to the value of the function at x equal to a. Clear? So viewers, we have discussed the continuity of a function. Now let us take some examples to further discuss the continuity of a function. Viewers, let us take this example. Discuss the continuity of the function fx at x equal to 0 if fx is defined by 2x minus 1 if x is less than 0, and 2x plus 1 when x is greater than or equal to 0. So here we have x is equal to 0. So for this part here, the function is fx is equal to 2x minus 1, and in the right of x equal to 0, including this point, the function is defined as fx is equal to 2x plus 1. So now what we will do, we'll find the left hand limit and the right hand limit. So let us find. So the left hand limit is limit x tends to 0 minus of fx. Now we'll put x equal to 0 minus h. Clear? So when x tends to 0, h tends to 0 and h is greater than 0. So therefore left hand limit is limit h tends to 0. Now this expression becomes h tends to 0, because when x tends to 0 minus, then h tends to 0. So we have f of 0 minus h. For x we have substituted 0 minus h. Now for the values of x which are less than 0, the function is defined by this expression. So we'll substitute here this. So limit h tends to 0. So this is f of 0 minus h. So here we'll have 2 times 0 minus h minus 1. Now this is limit h tends to 0. This is minus 2h minus 1. And we substitute the value of h equal to 0 here. So we have minus 1. Now similarly we find the right hand limit. Again we will take the right hand limit as x tends to 0 plus fx. So we'll substitute here, x is equal to 0 plus h, and as x tends to 0, h tends to 0. So here we have 0 plus h, because x is 0 plus h. Limit h tends to 0, f 0 plus h. Now for x greater than or equal to 0, it is defined by 2x plus 1. So here we have 2 times of 0 plus h plus 1, which is equal to limit h tends to 0, this is 2h plus 1. And if we substitute the value of h equal to 0 here, so we are left with 1, because this is 2 times 0 plus 1, this is equal to 1. Similarly here we have minus 2 multiplied 0. When we substitute h is equal to 0, minus 1, so we have minus 1. So viewers, here we see that the left hand limit is equal to minus 1, and this is left hand limit is minus 1 and the right hand limit is 1. So this is 1, and these two are not equal. The limits exist, but they are not equal. So therefore the limit x tends to 0 fx does not exist, and hence we conclude that fx is not continuous at x is equal to 0. Clear? Viewers, let us take this example. Show that fx is equal to x over mod x when x is not equal to 0, and fx is defined as fx equal to 1 when x is equal to 0. So let us prove that this function is discontinuous at x is equal to 0. So let us find the left hand limit. So the left hand limit is, as we have done in the previous example, this is x tends to 0 minus fx. Then we will write h tends to 0 and f of 0 minus h. Clear? Then we have substituted here x is equal to 0 minus h. When x tends to 0, h tends to 0 and h is greater than 0. So here we have limit h tends to 0, f of 0 minus h is f of minus h. Now here the function is defined as x over mod x when x is not equal to 0. So we'll utilize this function here. So this is limit h tends to 0, f of minus h is minus h over minus h, and this is equal to limit h tends to 0, this is minus h, mod of minus h is plus h, so h and h get cancelled, so this is limit h tends to 0 of minus 1, so we have minus 1. Clear? So this is the left hand limit. Now let us find the right hand limit. So the right hand limit is here. Again here we will write the positive sign, so we have x tends to 0 plus fx. Clear? So this is limit h tends to 0, f of 0 plus h. Clear? So again here we have also substituted x is equal to 0 plus h. X tends to 0 implies h tends to 0 and h is greater than 0. H is a very small quantity. So this is limit h tends to 0, f of h. Now again we'll utilize this function here, because fx is defined as x over mod x for x not equal to 0. So this is limit h tends to 0. F of h is h over mod of h. So this is limit h tends to 0, h over h. Mod of h is h, because h is a positive quantity. So mod of h is equal to h. So h get cancelled. We are left with 1. So this is equal to 1. So viewers, here we observe that this value and this value are not equal. That is, moreover, f of 0 is 1. Clear? So the left hand limit is not equal to the right hand limit, because the left hand limit is -1 is not equal to 1. So therefore the limit x tends to 0 of fx does not exist. Clear? And hence fx is discontinuous at x is equal to 0. Clear? Viewers, let us take this example. Here we have to show that this function fx equal to 2x minus mod of x is continuous at x equal to 0. So what we'll do, we'll find the left hand limit. So limit x tends to 0 minus fx. So this is limit h tends to 0 of 0 minus h. Clear? Now we have limit h tends to 0 f of minus h. So we have limit h tends to 0, f of minus h is, we'll substitute minus h for x. So we have 2 of minus h minus of minus h. Clear? So h equal to 0 gives us, this is 0, this is 0. So we have minus of 0 minus 0. Clear? So this is equal to 0. Clear? So the left hand limit is 0. Similarly, the right hand limit x tends to 0 plus of fx. Clear? Now here we'll write h tends to 0 f of 0 plus h. See, here we are substituting x is equal to 0 minus h. As x tends to 0, h tends to 0 and h is greater than 0. Similarly here, what we are doing, 0 plus, we are substituting x equal to 0 plus h. And when x tends to 0, h tends to 0 and h is greater than 0. So here we have limit h tends to 0, 0 plus h is f of h. So f of h is, we'll obtain it from here. So this is limit h tends to 0, 2 times of h minus mod h. Now we'll substitute h equal to 0 here. So we are left with this expression. So it is 0. Now here we see that these two limits are same. That is, left hand limit is equal to right hand limit. So therefore limit x tends to 0 without any sign here, fx exist. Clear? Exist and equal to 0. Clear? Now let us find the value of f naught, f of a. F of a. F of a is f of 0. So f of 0 is, we'll substitute here x equal to 0. So we have 2 times 0 minus 0. So it is 0. So we see that left hand limit is equal to right hand limit is equal to f of 0. So therefore all the conditions for continuity of a function are satisfied, and hence fx is continuous at x equal to 0. Clear? So viewers, let us take this example. Here we have fx is equal to sine 3x over x for x not equal to 0 and fx is equal to 1 or x equal to 0, and here we have to prove that it is discontinuous at x equal to 0. Clear? So what we will do, we'll again find the left hand limit, and the left hand limit is x tends to 0, because here the point of consideration is 0, so x tends to 0 minus fx. Now we'll write it as h tends to 0 as we have done in our previous example. So this is f of 0 minus h. So this is equal to limit h tends to 0 f of minus h. 0 minus h is minus h. So limit h tends to 0 f of minus h. Will substitute the value of x is equal to minus h in this function. So we have sine of 3 minus h over minus h. So this is limit h tends to 0 minus is we have a minus of sine 3h over minus h. Why? Because sine of minus theta is equal to minus of sine theta. Clear? So here we have minus and minus get cancelled, so we are left with limit h tends to 0 sine 3h over h. Now we divide it and multiply it with 3. So this expression becomes 1. So 1 multiplied 3 equal to 3. Why it becomes 1? Because we know that limit theta tends to 0 and sine theta over theta is equal to 1. So here h tends to 0, so sine 3 theta over 3 theta, this is equal to 1. So 1 multiplied 3 is equal to 3. Now similarly we'll have the left hand limit, right hand limit. So here we have x tends to 0 plus of fx. So here we have h tends to 0 f of 0 plus h. Clear? So we have limit h tends to 0 f of h. So we'll write it f of h is sine of 3h over h. So again we'll do the same thing as we have done in the calculation of left hand limit, that is we'll divide and multiply by 3. So sine 3h over 3h multiplied 3. Now this term becomes 1 by this formula. So we have 1 multiplied 3 is equal to 3. So we see that this is 3 and this is 3. So left hand limit is equal to right hand limit. Therefore the limit x tends to 0 of fx exists and equal to 3. Clear? But here we see that for x equal to 0, this is an important thing here. For x equal to 0, f of 0 is 1. So therefore left hand limit is equal to right hand limit, but they are not equal to the value of the function at x equal to 0. Clear? So therefore limit x tends to 0 of fx is not equal to f0. Hence fx is not continuous at x is equal to 0. So therefore fx is discontinuous at x is equal to 0. Clear? So viewers, let us take one more example. Now this example is slightly different from the examples which we have just solved. For what value of k? Here we have to find the value of k. This k. Is the following function continuous at x is equal to 2? So here the point of consideration is x is equal to 2, and the function is defined as 2x plus 1 for x less than 2, fx is equal to k for x equal to 2, and 3x minus 1 for x greater than 2. So here we have to find this unknown k. So we have to find the value of k. So again this function is given to be continuous at x is equal to 2. So let us first find the left hand limit. So the left hand limit is x tends to Here the point of consideration is 2, so we'll write 2 minus of fx. Clear? So we'll have here h tends to 0, so f of 2 minus h. Clear? Because here we have substituted x is equal to 2 minus h. So as x tends to 2, h tends to 0. Clear? When x tends to 2, h tends to 0, and h is always greater than 0. So here we have limit x tends to h tends to 0, f of 2 minus h. Now this is limit h tends to 0, f of 2 minus h. For x less than 2, the function fx is defined as 2x plus 1. Clear? So here we have 2 times of 2 minus h plus 1. Now we'll substitute the value of h equal to 0 here. So we have 2 minus 0 plus 1. Clear? So this is 2 to the 4 plus 1. This is 5. Clear? Now let us find the value of right hand limit. So the right hand limit is limit x tends to 2 plus fx. So again we'll substitute x is equal to 2 plus h. So when x tends to 2, h tends to 0 and h is greater than 0. So this expression becomes h tends to 0 and f of 2 plus h. Now for all x greater than 2, the function fx is defined as 3x minus 1. So this is limit h tends to 0. This is 3 times of 2 plus h minus 1. Now when h is equal to 0, the limit becomes this. This is 3 to the 6, 6 minus 1, 5. So we see that these two values are equal. That is left hand limit is equal to right hand limit. So therefore limit x tends to 2 of fx is equal to 5. Now f of a. Now f of a, that is f of 2. F of 2 is given as f of 2. When we'll substitute as x is equal to 2, here x is equal to 2, fx is defined as k. So therefore f of 2 is equal to k. Now for fx to be continuous at x is equal to 2, the condition is limit x tends to 2 of fx must be equal to f of 2. So this limit is 5 and f of 2 is k. So therefore k is equal to 5. Clear? So viewers, let us take the last example of today's lecture, that is find k for which fx is equal to kx plus 5 for x less than or equal to 2 and fx is equal to x minus 1 for x greater than 2. So this function is continuous, is given to be continuous at x is equal to 2, and we have to find this unknown value x. So k is the unknown. Clear? So what we'll do, we'll do the we'll find the left hand limit and right hand limit. So left hand limit is limit x tends to, the point of consideration is 2, this is 2 minus of fx. So limit h tends to 0 of f of 2 minus h. Again x is equal to 2 minus h. As x tends to 2, h tends to 0 and h is greater than 0. So here we have limit h tends to 0, f of 2 minus h. So f of 2 minus h is here for x less than 2, the function is defined as kx plus 5. So here we have kx. For x we have 2 minus h plus 5. So when we substitute h equal to 0 here, so we have k 2 minus 0 plus 5. So this is 2k plus 5. Clear? Now let us find the right hand limit. So for right hand limit, what we will do, we will find limit x tends to 2 plus fx. Clear? So limit, this is h tends to 0, this is f of 2 plus h. Again we'll substitute x is equal to 2 plus h. When x tends to 2, h tends to 0 and h is greater than 0. So limit, this is h tends to 0, f of 2 plus h. Now when x is greater than 2, fx is defined as x minus 1. So this is 2 plus h minus 1. So h0, we'll substitute h is equal to 0 here. This is 2 plus 0 minus 1, that is 2 minus 1 is 1. Clear? Now again from this definition here, for x equal to 2, the function is defined as fx is equal to kx plus 5. So therefore f of 2 is 2k, because here x equal to 2, for x equal to 2 it is kx plus 5, so this is 2k plus 5. Now for fx, to be continuous at x is equal to 2, limit x tends to 2 minus fx must be equal to limit x tends to 2 plus fx must be equal to f of 2, or in other words we can say that the left hand limit must be equal to right hand limit must be equal to f of 2. Clear? So left hand limit is 2k plus 5, right hand limit is 1, and f of 2 is 2k plus 5. Now we'll take this equation, that is 2k plus 5 is equal to 1. So 2k is equal to 1 minus 5. So 2k is minus 4, k is minus 4 over 2. So k is minus 2. So this is the required value of k, which makes this function continuous. Clear? Thank you.